Good morning. Welcome to Sunday Symposium at Oakmont. This is Jeff Newman. Pleased to welcome Clarke Knight this morning. Clarke comes with an impressive resume, and I'll go ahead and read the bio we were provided. Clarke Knight is in her 5th and final year as a PhD student at UC Berkeley in environmental science. She studies forest response to climate change, past and present, and she conducts research in California's mixed conifer forests, where disturbance regimes, especially wildfire, drive community composition and ecosystem function. In addition to research, Clarke is committed to the application of science to our toughest environmental challenges. For example, she was part of a team of scientists writing California's 4th Climate Assessment Report, one of the largest collections of actionable climate change research in California's history. Before Clarke started her PhD at UC Berkeley in 2016, she completed 2 master's degrees from the University of Oxford and a BA in chemistry from Smith College. She loves living in Berkeley and is an avid hiker and landscape photographer. Welcome, Clarke, and go ahead. Thank you.
Thank you so much for that introduction, Jeff. I appreciate it. And thank you both for having me here today. I'm really excited to talk at the Oakmont Symposium. So I'll go ahead and share my screen now, and I will get started on my talk. So I hope you can see my screen now.
Looks good.
The title of my talk is Earth's Time Machines, How We Understand the Ecology of the Past. And I'm excited to share with you today some elegant and important research that's happening in the field of paleoecology. Paleoecology is the study of ecosystems in the past. And I want to talk to you today about a question that has been driving my curiosity for the past several years. And that question is this: what can the past tell us about what's going on today and the future? And to answer this question, I will be telling you 3 different stories from recent research findings, and I'll be explaining the meaning of those findings. And after that, I will be discussing how the recent pandemic of COVID-19 has been influencing climate change. And so with that, I want to take you to the first place, which is Antarctica. I'm sure you know Antarctica, and it's a frozen, desolate place that's dark for half of the year. Only the hardiest animals survive in such a landscape. And what you don't notice here are plants. There's nothing green growing on Antarctica. Scientists have long been intrigued by the history of the so-called white continent. For instance, they know that ice sheets once covered Antarctica, and they started building about 35 to 40 million years ago. But scientists have also wondered what Antarctica was like much before this time, and what its history can tell us about contemporary climate change. So in 2012, a group of scientists went looking for fossils that could tell them more about Antarctica's ancient history. They knew from previous research, for instance, that the fossils they needed were in Western Antarctica, which is south of Chile. And so they reasoned that they could drill down deep into the ocean and get a sample of the Earth's crust, much like oil rigs do. And they were able to get a research vessel. It's actually called the Polar Stern, and you can see it here. And this research vessel brought them to the extreme underside of our planet. But they still needed a way to get the fossils. What they ended up doing was using a robot. It's called Mariam Nebo 70, and you can get an idea of what it looked like from this picture on the left. This is a really cool robot. It's remotely operated, and it's a 10-ton device that sits on the seafloor and crawls around. It's attached by an electronic umbilical cord to the research vessel. You can see here on the right a picture from the seafloor taken by the Nebo robot. And so what these scientists did is they took this robot on their research ship, and they wanted to find an area of the Earth's crust that corresponded to 90 million years ago. And they were able to find that piece right here. And now 90 million years ago is from a time period called the Middle Cretaceous, or the Turonian-Santonian age. And what they did is they took their robot and they drilled for 30 meters. And what they recovered was remarkable. It was a 3-meter long core with a network of intact fossil roots as well as pollen grains. And I'll be explaining in a few slides what pollen grains are. And when they pulled this core to the surface, the scientists on the research ship were blown away by what they found. They knew they had something special, but they did not want to disturb their sample. So instead, they flew with their core back to Germany, where they took a CT scan. Now, you've probably heard of CT scans in the context of the medical field, but you can also use them for sampling. And so here's a picture of the CT scan of the core. You can see at the top, there's this layer that's shown in yellow, and that corresponds to the area of sediment just above the layer that they were shooting for. And in green, they've colored here the picture of the fossil roots that I mentioned earlier. And this is remarkable because you usually don't get fossilized roots when you look for sediment cores. And this core contained, as they found out later, the kind of plants and flora that would only have survived and grown in a rainforest. And so what I'm telling you is that Antarctica was once a lush rainforest. And this was astonishing to me when I first learned about it. This research has come about in the past couple of months. And here you can see an artistic drawing from James McKay about what this kind of landscape might have looked like. And you also might be wondering, how on earth could a rainforest exist on Antarctica? These scientists also pose that same question. So they did some modeling to understand what the carbon dioxide concentrations must have been like on the planet in order to facilitate the growth of a rainforest. And what they found is that about 90 million years ago, the CO2 levels in the atmosphere must have been upwards of 1,600 parts per million of carbon dioxide. For reference, today's levels of carbon dioxide are at about 418 parts per million of CO2. So this means that the atmosphere 90 million years ago had 4 times as much carbon in it to get a landscape such as this on Antarctica. And this isn't just a wonderful fact about our planet, that we could have a rainforest, a lush place growing on Antarctica. It's also vital information that provides insight about our rapidly warming planet that's happening today. For instance, a question that scientists have been thinking about for the past decade or so is, why is it that the polar regions, so Antarctica and the Arctic, are prone to warm faster than other parts of our globe? And you can see here a picture of what's happening. So the scientists call this phenomenon amplified polar warming. And I want to walk you through what this graphic is showing. So this is a picture of the Earth. It's taken from Berkeley's Earth Observatory. And it's showing different colors here, -10 to 0, all the way to +10 in dark red. And what this means is it's a temperature anomaly. So they're looking at the temperature from the past couple of months. You can see here May 2020 on the top right. And they're comparing recent temperatures observed on Earth in May compared to the relative temperatures that occurred between 1951 and 1980. And so this temperature anomaly represents the difference between what we see today and this previous time period. What I want you to notice about this is that the poles are shown covered in these big dark red splotches. And that means that the poles are actually far warmer, upwards of 10 degrees warmer than they have been in the past. You can see in contrast that places closer to the equator are not quite so anomalously warm. So what is the import of this? Well, if you think about what's happening with global climate chaos, is that you're starting to see warming effects hitting different parts of our globe at different times and in different magnitudes. You might be asking yourself, why would the poles get warmer more quickly than the equator, say, or other places? And that has to do with a pretty simple phenomenon. There are some other things involved, but one of the most simple explanations can actually be thought about in pretty simple terms. Just imagine if you were going to leave your house on a very hot summer day. would you want to wear a very darkly colored shirt or a light colored shirt? If you wanted to keep cool, you would wear a lightly colored shirt. This would help reflect the sunlight off of you. That same phenomenon of the importance of reflectance is occurring at our poles. So because Antarctica is mostly covered in snow and ice, that ice and snow is reflecting between 50 to 70% of the sunlight that hits it. However, that ice is surrounded by very dark ocean water, and that ocean water doesn't reflect sunlight very well. So when you have these anomalously high temperatures, is you get a little bit more of that ice melting, which then converts it into ocean water that's darkly colored and that absorbs sunlight, which then causes the ice to melt a bit more. And so what I'm telling you is that there is a positive feedback loop occurring, such that when you have these higher temperatures, you start to rapidly speed up the deglaciation of the poles. And so understanding a bit about what was happening with Antarctica in the past gives us insight into things that are literally occurring today. And so I want to introduce you to another really important aspect of paleo data, which is the pollen grain record. And pollen grains are something you're probably pretty familiar with. I'm going to just show a very brief video here of pollen grains coming off a tree. Now you can see a massive cloud just come off of that tree. And honestly, when I see this video, it makes me want to sneeze. And if you imagine just the sheer amount of pollen that came off the tree in one go, now start to imagine what it might be like with a forest full of pollen. That's certainly a ton of pollen. And I want you to think about what happens to that pollen. So pollen grains are produced by vascular plants like trees as part of their reproductive cycles. And those pollen grains are designed to disperse widely throughout the landscape. Some of those pollen grains go on to achieve their biological purpose, which is pollination. But the vast majority of pollen grains don't end up as pollinators. Where they do end up is in places like your nose and giving you allergies, or in collecting basins, such as lakes. The vast majority of pollen grains are found in places like lakes. And you can see here a picture of Crater Lake in Oregon with pollen swirling on the top. Over time, that pollen will fall through the lake water and become incorporated into the lake sediments in chronological order. And it's in the sediments that pollen really shows how remarkable it is. Here's an up-close view of pollen grains. You can see that they're quite aesthetic and they come in different shapes and sizes. This is really important because it allows scientists to correlate the shapes and sizes of pollen grains that they find with real tree taxa around those lake environments. So if you see a grain and you know what tree it corresponds to, then you also know the kind of trees that were occurring around that lake in the past. And another really remarkable thing about pollen is that it's able to survive for millions of years in these sediments because it is made with one of the most durable materials ever found in nature. And it's a substance called sporopollenin. And if you remember back to my example with Antarctica, they found fossilized roots, but also fossilized pollen grains that were upwards of 90 million years old. Those pollen grains were preserved because of this hard exterior that they have made of sporopollenin. And I just want to say for my own self that collecting sediment cores is really fun. You can see here a picture of some research scientists in the Arctic actually, and they're taking a sample from that lake. And it involves basically being in a boat all day to get this kind of a sample. So you have a coring device, which you can see here, and you very carefully position your boat in the center of a lake. And then you drop your coring device over the side and you pull up sediment because you create a vacuum with the top of the core and the sediment that you shove it into. And these sediment cores are really cool when you look at them up close. So here's a picture of a sediment core that's been split in half. And I want you to notice, first of all, that it has these different colored bands. Those different colored bands correspond to different sedimentation events that occurred at that lake. And each of those layers corresponds to a different time period. So you need isotopic analysis to understand the age of the sediment, and that's a very important part of this analysis, is getting time periods on those sediment layers. I want to reiterate what's happening with pollen, and that there's pollen grains embedded throughout this, this whole core. So pollen grains come off the trees and they're incorporated into the lakes, and then over time incorporated into the sediments. The same phenomenon is actually occurring with charcoal. And this is really important because charcoal is a proxy for fire. And in many locations and landscapes, fire is an integral driver of community composition over time. And it's responsible for consuming vegetation and allowing new vegetation to grow. So if you have an event, a fire event, say caused by lightning, that burns a large area, pieces of charcoal are created from that fire event. And some of that charcoal can fly through the air, say, and land in a lake. Some of that charcoal can also be washed into the lake through rainfall or other erosional events. And so in that way, charcoal can become just as valuable as pollen. And here's some up-close images of pollen and charcoal. So on the left-hand side, you can see pictures from my research, and this grain at the top left is what the pollen grains for Pseudotsuga menziesii, or Douglas fir, look like. This is a tree you're probably very familiar with as California residents. On the lower left, you can also see a pollen grain that looks a bit like Mickey Mouse ears, and this means it's a pine pollen grain. So this comes from a tree like sugar pine or Jeffrey pine. And now on the right-hand side, you can see examples of charcoal. So these smaller charcoal pieces are called microcharcoal, and these larger charcoal pieces are called macrocharcoal. Both of them are deposited in lake sediment cores. And so now I want to get back to the storytelling, and I want to tell you about a really elegant example of using the charcoal record to understand important events in human history. So this is a 3D model of a stone stele, which is a stone tablet, and it's been taken from present-day Guatemala from an ancient Mayan ruin. Archaeologists have been studying this stone tablet, and they found that there is an intriguing inscription on it. And that intriguing inscription reads that the city of Balamjol, quote, burned for the second time. And with that record is a very precise date. The Mayans recorded it as occurring on May 21st, 697. This record has long been mysterious to modern archaeologists and specialists in Mayan affairs. First of all, where is Balamjol? And second of all, what kind of burning took place there? So several years ago, a research team led by Dr. David Wall of the USGS decided to go on a coring trip in Guatemala. And they found a really nice lake for getting a sediment core near the present-day city of Huitzna, which is a modern-day archaeological name for an ancient Mayan city. You can see it here in this top right of this map. And they were just on a routine coring trip, getting data, and they ended up finding a core that was very surprising. And here's a picture of that core. So on the left here, you can see the depth in centimeters of that core. So we're in a deeper part of the core here. It starts at 280 centimeters and goes to 330 centimeters. And you can see on the bottom right here, this acronym called CHAR, and it's in particles per centimeter squared per year. That's telling you the charcoal counts within this core. And what immediately stuck out to this researcher was the fact that at about 315 centimeters, there was a very large amount of charcoal deposited. And in fact, you can actually see the charcoal with your naked eye just by looking at this picture. And in the New York Times, Dr. David Wall was quoted as saying The fire was massive. It was unlike anything I've seen in the 20 years I've been doing this. So these couple centimeters here of charcoal is truly remarkable. And it represents a massive, intense fire that took place on the landscape. But what's also really important about this sediment core is that each amount of sediment was deposited very rapidly. And they found this through further analysis of the core. And by that I mean that each centimeter you see here represents less than a decade of time, perhaps close to just 1 year. This means that the sediment core represents an extraordinarily detailed record that can be tied closely to dates and other records that are important to us. And so, as I mentioned earlier, that dating sediment cores is a very important part of the analysis. Well, that definitely came into play here. So this team of scientists were able to use isotopes to get a very accurate age model of this core. And they found that the sediment layer of charcoal was likely deposited around 692 CE. And so you probably know where I'm going with this, but they concluded that there was likely a massive fire event that was deposited very quickly. And coupled with the synchronicity of the burn statement from the stone stelae, they were able to provide strong evidence that there was a fire that razed Balam Jol on the 21st of May. And this is the first time a stone record has been linked so convincingly to something from the sedimentary record. And the image I'm showing you now is a picture of LiDAR. And LiDAR is very similar to radar. So you're seeing a canopy level view of Mayan ruins. You can see some of them are circled here in yellow and have numbers next to them. And this is a view of the ancient Mayan ruins that you would not have if you were just walking around in the rainforest. They're showing you far more detail about the structure underneath the jungle. And I just want to highlight that this part here is very likely the city of Balam Jol that was described in this stone tablet. And this was not known beforehand, nor was it known that this massive fire event was likely part of an instance of total war within the Mayan community. And I'm sharing this research because I think it's a very elegant combination of using something that is in the written record and is known from the archaeology research, and combining that with the sedimentary and environmental evidence that can be found on the ground. And although the Mayan civilization is no longer around, we can use very similar techniques to understand what's been going on in the past environment in other places that we care a lot about. And that brings me to California, because there are many vital land management questions that are continuing today that can be addressed through paleo records. And one of the most important topics in California is water. Water has been a particular concern, especially since the 2012-2015 drought that spurred numerous conservation efforts. For example, there was the first ever mandatory statewide water restriction during that drought event. And there were many debates, some of which continue to this day, about how to share limited resources among competing interests, whether it's drinking water for people or water for agriculture and animals. What's interesting, however, about drought is that one of the first harbingers of it derives from estimates of winter snowpack. You can see here in the picture, this is the Sierra Nevada mountains in the winter of 2015. There's a paltry amount of snow compared to previous estimates of snow in the area. The Sierra snowpack is really important in California. It plays a critical role in replenishing the state's water reservoir and provides something like 30% of the state's water supply. In recognition of this importance, scientists have been taking snowpack measurements every year since 1930. However, the snowpack has been happening a lot longer than just 1930. So one question that becomes important is understanding what the snowpack level was like before instrumental records are available. And one of the key questions in this was understanding just how unusual was this 2012 to 2015 drought event? Well, the field of dendroclimatology can help answer this question. Dendroclimatology is the science of determining past climates from tree rings. And early dendrochronology started with the ancient Greeks, who first observed that tree rings form mostly on an annual basis, and they noted that the width of rings seemed to vary from year to year. This was an important insight. During the Renaissance, Leonardo da Vinci associated tree ring variation with change in the environment at the time of ring formation. This was another very important piece, very important insight. And it wasn't until the early 1900s that a man by the name of Andrew Ellicott Douglas noticed not only variation in tree ring width, but also that this variability was similar between multiple trees growing in the same area. And he surmised that there must be some specific environmental component that could cause multiple trees to respond in the same way and produce rings of similar sizes. And what he found is that variable was climate, specifically rainfall patterns. And so I want to walk you through what's going on in this picture. So you can see here a stump of a tree that's been cut. And here we're just looking at a slice that starts at the center of the tree, which is called the pith, and moves outwards towards the bark, which you can see here at the top. Different kinds of tree rings are shown, where you have wider tree rings, and those represent good growing conditions, i.e. times when there was plentiful rainfall for the tree to grow well, compared to thinner rings, which represent harsh growing conditions, likely times of water restriction and stress on the tree. And you can also note that there is a different color to each part of the ring. So you have this lighter color, which is called early wood because it's put on early in the season, and then immediately after a very thin dark ring, which is called late wood. And taken together, that represents one tree ring. And so scientists wanted to know and to use tree rings from California to understand what winter snowpack might have been like over long periods of time. And so they decided to use the blue oak. The blue oak is an endemic species in California. You can see it here on the left. And it's a very beautiful tree. And another interesting thing about the blue oak is that its distribution forms this nice ring around the Central Valley. And so you're able to understand what was happening in the Sierra Nevada, which it lives against. It has many populations right up against the Sierra Nevada by looking at tree rings from this species. And you can see here these little triangles encircling the Central Valley. Each of those triangles represents a site where scientists were able to take a tree ring from an old growth blue oak. So that is a tree that's very old. And they were able to look at and compare these tree rings from, I think it was upwards of 35 sites, and take them together and create this portrait of 500 years of ecological change. And so I want to show you what some of those tree rings look like. So their data set allowed them to look at different time periods. Specifically, they were able to go back to the 1500s. And this is an example of some of those tree rings in a highly zoomed in way. So you can see we start here on the left at 1581, and we continue to the right to 1587. What I want you to notice is that 1583 is a very wide ring, which means it was likely a very wet year, and that tree grew pretty well. Compare this then with 1585, which is a very thin ring, and shows probably that they're having a very dry year. So when we look at this data taken together, we get an image like this. And so I first want you to note that at the bottom here, we have the data set starting in the year 1500. And then it goes every 100 years, you can see they've marked all the way through the year 2015. And on the y-axis, we have what's called the 1st of April snow water equivalent. The snow water equivalent is just a way of understanding snowpack. So you can think of it as just meaning snowpack. And what I want you to notice here is that the tree ring record is shown in these peaks and valleys shown in black. This is compared with the instrumental record, which starts in 1930, as I mentioned earlier. And you can see that the black and red overlap each other nicely. And that's a relief because that means the instrumental record is corresponding very well and corroborating the tree ring record. And what you can see here on the bottom right is the data point from 2015, and it takes you really low. So lower values are indicating drought events. And you can see here, in fact, that 2015 is very, very low. And if you follow this red line, you're able to compare that 2015 data point across the entire data set. And as we go back in time, as we get to the 1580s, and the 1580s are really the only time period in the past 500 years that even approach the magnitude of the drought event that we occurred in the 2012 to 2015 period. I think that this is quite interesting because it really contextualizes what just happened in California from 2012 to 2015. And in fact, it can help land managers, specifically those involved in water management, understand what might happen after this drought event by looking what goes on in the 1600s, as well as just asking better questions based on the fact that they know this drought event is unprecedented in the last 400 years. And so I want to leave you with some of the take-home messages from Earth's time machines, as I call them, or the natural archive. The first thing being is that they're important. They're really key to helping us understand not only more about our world, but also helping us find answers to questions that are occurring today. For instance, they help us understand how ecosystems have responded to past disturbance. For instance, with really high carbon dioxide levels, you can get situations where you have lush rainforests growing at the southern pole. Secondly, natural archives are important for understanding the context of current major disturbance events, like the 2012 drought. And they can also reveal potentially unexpected legacies of those events. And then lastly, they help us expand our idea of what a baseline is, because baselines are typically those conditions for which we have records available to us in the written record or the instrumental record. But by extending that further back, we can determine whether our baseline conditions are actually feasible or even desirable as management goals. And so I hope you've taken a lot away from these couple of stories, and I now want to switch to talking about the impact of the COVID-19 pandemic on the global climate problem. So you've probably seen some images like this floating around the news in the past couple of months. This is just a picture of some animals that escaped in Wales, actually, and were taking over the streets, which were empty of people. This is happening in a lot of different places, and I think it's hitting home this idea of what is happening when people aren't around, or people are not out as much. And you might be wondering if this has had a positive impact on our global emissions, since we're working from home now, for instance, and we're not taking as many flights. So I pose this question to you. Is the COVID pause climate friendly? Is the fact that we are confining ourselves more at home having a positive impact on the climate? Well, in the yes category, there are some good reasons why this might be true. For example, daily emissions are down by about 17% according to recent reports. This is the largest annual drop in industrial emissions since World War II, and that's probably a good thing. And lastly, the COVID pause might be climate friendly because it's shown just the sheer amount of global coordination and solidarity that will be needed to confront such global challenges. But I want to interrogate this idea further and think about ways in which this might not be such a good thing overall. First of all, the drops in emissions have had relatively little impact on the overall CO2 concentration in the atmosphere because climate change is a cumulative problem. So the 418 parts per million of CO2 are already in the atmosphere, and that's not going down just because we've been working from home more and not driving our cars as much. Secondly, people are still using heat and power in their homes, sometimes more so, which contributes to CO2. And in fact, there was a news story that came out just today in the New York Times by the title of "Emissions Are Surging Back as Countries and States Reopen." I encourage you to read this piece. And in fact, it's showing, now that we have data from the end of May and the beginning of June, just how much we dropped from the closings in March and April, and now the effect of rebounding. So this is work that's based on a recently published paper, which you can read here. And you can see that they've broken up the different kinds of emissions by different sectors. So here on the top left, we have road transportation and shipping, and you have the drop in MTCO2, which stands for metric tons of carbon dioxide. And you can see with by middle of March, as we had this really big drop in road transportation and shipping emissions, as we expected, as the confinement continued. This blue line here is showing you the median climate, the median estimate, which we can see there's actually been an uptick and now a really rapid change in the positive direction in the past month. This story is similar across different sectors. It's true in industry, it happened in power, it happened in aviation, and it also happened in public buildings. The drop in emissions we saw are all now surging back. Lastly, this idea of residences or homes, they never had an emissions drop. So you can see, in fact, during confinement, there's likely an uptick event where people were using more energy in their homes. And so all of this is to say that a pandemic is probably the worst way to reduce emissions. I don't think that there's much to celebrate here. And I think that the drops in emissions that we saw because of confinement only reveal this deeper truth about what's happening with climate chaos. And that's this. The climate chaos is much too large to be solved simply by abandoning planes and not driving to work every morning. We still have about 90% of the necessary decarbonization left to do to get back on track for the Paris Agreement, which has a very ambitious goal, but is probably doable, which is a climate increase of only 1.5 degrees Celsius above and beyond the Industrial Revolution. What this means, I think, ultimately, is that our use of carbon as a fuel source is so deeply embedded in how humanity runs itself that emissions are just going to keep happening unless we change the underlying systems. And so the trajectory of global emissions in the years ahead is probably going to be heavily influenced by the stimulus measures that we take on now. For instance, we could seize this moment by investing in cleaner energy sources in order to prevent an even larger rebound in fossil fuel use. And so I want to leave you with this last cartoon image, which I think summarizes what I've been talking about pretty well. You can see here we have the COVID-19 wave, followed by a recession, a global recession of some unknown magnitude, but it's likely to be large, followed up by climate change, which we know from the scientific literature will definitely be big. And I want to leave you with this quote from The Economist that I read a couple of weeks ago. And the quote is this: "Disasters long talked about and long ignored can come upon you with no warning, turning life inside out and shaking all that seems stable. The harm from climate change will be slower than the pandemic, but more massive and long-lasting. If there is a moment for leaders to show bravery in heading off that disaster, this is it. They will never have a more attentive audience." So I want to thank you for your time, and I look forward to answering your questions on Sunday, June 28th. Thank you so much.
Thank you, Clarke. That was fascinating. Really wonderful. I appreciate your talk, and I will end the recording now.